Aromatic compounds and amines. So the main thing about this topic is benzene, obviously. So benzene is a flat molecule containing a ring of carbon atoms with hydrogen sticking out on a flat plane. Benzene structure's plain cyclic structure has 6 carbon atoms joined together in a flat ring. Planar cyclic structure, 6 carbon atoms joined together in a flat ring. Each carbon atom forms single covalent bonds to carbons on either side of it and to one hydrogen atom. Final unpaired electron on carbon atom located in a p orbital sticks above/below the plane of the ring. P orbitals on each carbon combined form a ring of delocalized electrons. All carbon-carbon bonds in the ring are the same length, 140 pm. Why is benzene more stable than cyclohexa-135-triene? Ring in cyclohexa-135-triene is made of alternating single and double bonds. Experimental enthalpy of hydrogenation of benzene is minus 208 kilojoules mole per minus 1. The actual enthalpy of hydrogenation of benzene is less exothermic, about 152 kilojoules per mole to power minus 1. You need more energy to break bonds in benzene, therefore benzene is lower in energy than cyclohexa-135-triene. Benzene is more stable as of the delocalized ring of electrons. Aromatic compounds containing a benzene ring, arenes. Aromatic compounds are derived from benzene. Phenylamine. Phenol is a benzene ring with OH group attached to it. Phenylamine is a benzene ring with NH2 group attached to it. Why do arenes, aromatic compounds, undergo electrophilic substitution? Benzene ring is a region of high electron density. It attracts electrophiles. Therefore, one of the hydrogens is substituted for an electrophile. That's the whole point of electrophilic substitution. One of the hydrogen atoms is substituted for electrophile, or one of the functional groups is substituted for electrophile. However, arenes can't undergo electrophilic addition. That could be exam questions state why arenes can't undergo electrophilic addition, as it would destroy the ring of delocalized electrons because it's so stable. High electron density, if it undergo electrophilic addition, it would destroy the ring of delocalized electrons. Phenol cross acylation produces phenol ketones, uses the acyl chloride as an electrophile, and the halogen carrier is AlCl3. Acyl chloride is electrophile, halogen carrier AlCl3. Phenol cross acylation produces phenol ketone used to add an acyl group RCO- to benzene ring. Once the acyl group is added, side chains. So yeah, what's the aim of phenol cross acylation? To add an acyl group to benzene ring. Once the acyl group is added, side chains are modified using further reactions to make useful products. So 2 key characteristics of the electrophile and phenol cross acylation. Electrophile needs to have a strong positive charge in order to attack the stable benzene ring, as most aren't polarized enough. It's made into a strong electrophile by using something called a halogen carrier, which is a catalyst. And the halogen carrier in phenol cross acylation AlCl3 acyl chloride is electrophile. Remaining content is mechanisms/equations, therefore will be in the mechanisms playlist. Yeah, just during my free period, and I was like, okay, I go through this mechanism, but it just doesn't make any sense. I'll go through later on, and I'll put it on that separate playlist, because I want to keep adding consistently to all 3 main playlists: the practicals, the mechanisms, and the past paper questions. Those are the main 3. Obviously, the rest are just all on specific topics. Those are every day as well, but those 3 I want to be extremely consistent with. Arenes can't undergo as dyes. Yeah, so why does it happen? Because dyes pharmaceuticals contain a benzene ring, but benzene is so stable, therefore unreactive, therefore is difficult to make chemicals containing benzene. That's why we use phenol cross acylation. Amines: if one or more of the hydrogens in NH3 is placed in an organic group, that's an amine. If one hydrogen is placed in an organic group, primary amine. If 2 hydrogens are replaced with an organic group, secondary amine. If 3 hydrogens are replaced with an organic group, tertiary amine. And then the final one, lone pair of electrons, nitrogen atom in tertiary amine bonding with a 4th organic group. Lone pair of electrons, nitrogen atom in tertiary amine bonding with a 4th organic group. This is called quaternary ammonium ion. Aliphatic amine, an amine in which nitrogen is bonded only to alkyl groups. Aromatic amine, an amine in which nitrogen is bonded to one or more aryl groups, so like the benzene ring, right? Quaternary ammonium salts uses cationic surfactants. Quaternary ammonium ions are positive charged, therefore they hang around near negative ions. Therefore, the complexes formed are called quaternary ammonium salts. Quaternary ammonium salts with at least one long hydrocarbon chain are used as cationic surfactants. The hydrocarbon tail binds to nonpolar substances, for example grease. The cationic head dissolves in water, therefore is useful in fabric cleaners/hair products. Also, the positively charged polyammonium ion NH4 plus ion binds to negatively charged surfaces, for example hair and fiber, so removing static, therefore is used in fabric conditioners. Why do amines act as weak bases? They accept protons and lone pair of electrons. Nitrogen atom forms a covalent coordinate bond with a H plus ion. Strength of base depends on how available the nitrogen lone pair of electrons is. More available the lone pair, more likely the amine is to accept the H plus, therefore stronger the base. More available lone pair, more likely amine to accept the H plus, stronger the base. Say key fact about a lone pair of electrons. A lone pair of electrons will be more available if the electron density is higher. Why primary aliphatic amine stronger bases in ammonia, and then weaker stronger base in aromatic amine? Primary aromatic amine, the weakest of them all, because the benzene ring, because remember, aromatic amine, an amine in which nitrogen is bonded to one or more aryl groups, or aliphatic amine, and an amine in which nitrogen is bonded to one or more only two alkyl groups. So aliphatic amine, nitrogen bonded to alkyl groups. Aromatic amine, amines bonded to aryl groups. Nitrogen bonded to aryl groups. Aliphatic amine, nitrogen bonded to alkyl groups. Aromatic amine, nitrogen bonded to aryl groups. Well, the primary aromatic amine, benzene ring draws electrons towards itself, and therefore nitrogen lone pair is partially delocalized onto the ring. Benzene ring draws electrons towards itself, and therefore nitrogen lone pair is partially delocalized onto the ring. So what happens? Benzene ring draws electrons to itself, nitrogen lone pair partially delocalized onto the ring. Therefore, electron density of nitrogen decreases, therefore lone pair is less available. Ammonia in the middle ground, and then primary aliphatic amines. Well, the alkyl groups push electrons on towards the attached groups, therefore the electron density, so alkyl groups push electrons to attached groups, therefore electron density on nitrogen increases, lone pair is more available. Finally, the lone pair of electrons also means that amines are nucleophiles, can act as nucleophiles. Amines are carboxylic acid derivatives. Carbonyl group pulls electrons away from NH2 group, therefore amines behave differently than amines. Why do amines behave differently than amines? Carbonyl group pulls electrons away from NH2 group. Amide, RC double bond O, NH2. N-substitute amide, RC double bond O, NHR. One of the hydrogens is replaced with alkyl group. And obviously, the remaining mechanisms, reducing nitrile and all that will be in the mechanisms playlist.